Lab 5, Magnetic Braking with Faraday by Anika Chawla. So the purpose of this lab is to explore the concept of Faraday's law by collecting observational data of a magnet falling through a conducting tube of aluminum foil, modeling the magnet-tube interaction computationally, and then comparing the computational predictions with the observed data. So here are some key concepts and equations. Magnetic flux is electric field dot the area vector. Faraday's law is negative d magnetic flux over dt. And then Lenz's law is that an induced current is always acting in such a direction as to oppose the motion or change causing it. So here's a procedure. First, mark the north pole of a bar magnet, hold the tube vertically and position the magnet just above the top, and record the magnet entering the top and leaving the bottom, and determine by looking at the video how long it took the magnet to fall through the length of the tube, and then repeat this 5 times for 5 data points and calculate the average time it took for the magnet to fall through the tube. So here are some key measurements for this experiment. The aluminum foil cylinder was 0.35 meters long, the width was 0.005 meters, the inner radius was 0.02 meters, and then the outer radius, which is the width plus inner radius, is 0.025 meters. And then the resistivity of aluminum foil is 2.65 times 10 to the negative 8th ohm meters. And then the magnet had a mass of 0.023 kilograms, and mu was 2.5 am squared, which is calculated in the third lab. And then, according to VPython, the calculated time was 0.24 seconds. And then the observational time was 1.33 seconds to fall through the tube on average. And as you can see, the magnet fell at a slower rate than if it were just a normal free fall. Like the magnet was kind of floating in the tube. So this means that the cylinder applied an upward force that countered gravity. So if we take a look at the code to just kind of understand what happened. So here we have mu over 4 pi, resistivity, gravity, and first we set the initial conditions of the tube, then we just have some numerical parameters of the simulation, and here we create the tube of aluminum foil as like a series of rings stacked along the y-axis. And then here we have the bar magnet. And then here we calculate the magnetic field of the bar magnet. So we can see that R hat is R over R mag, and then we use Biot-Savart law to find B, which is the magnetic field. And then we calculate the flux for each ring of the falling magnet. So like this is the numerator 1.5 times mu over 4 pi times 4 pi times the magnitude of the bar magnet's mu times distance times speed times the radius of the ring squared. And the denominator is the radius of the ring squared plus distance times 2 times 2.5. And then that returns the flux. And here we can see gravity is negative mg. The current is change in flux over the radius. And net force is going to be gravity plus the magnetic force. And we know that gravity is downwards because we multiplied it by -1 earlier. So yeah, that gave 0.24 seconds. And then for what if the resistivity of the conductor were reduced to be like as close as possible to 0, the magnet would fall more slowly since the magnetic force would increase, because current and resistance are inversely proportional, and current would increase, which would increase magnetic force, and the magnetic force is opposing the falling due to gravity. And then if holes and slots were cut into the tube, this would make the magnet fall faster because the magnetic force would decrease. Because as we saw in the code, we're kind of looking at the cylinder as like tons of rings stacked on top of each other. So there would be less complete rings that you would count. So this means that the magnetic force would be lower, less of a force would be countering gravity, so the magnet would fall faster.